Hi, my name is Eric Schneider, and I work together with Mono Trivedi and Joe Finn to bring you FMPGA, an FM synthesizer on an FPGA. This is a MIDI controller. It's not capable of producing any sound on its own. However, it is the conduit for producing sound. You see, a MIDI controller produces note on and note off messages, which can tell a synthesizer like ours, located right here, when to start playing a note and when to stop playing a note. And when playing a note, it can determine the pitch to play the note at. Now, in order to turn these note on and off messages into audible sound, you need to generate some sort of frequency and sustain it over a period of time. This is done through the use of a wavetable oscillator that outputs the exact pitch we expect to hear when playing a key. This is a very common solution to the problem that we're trying to solve. You can see that when we press a C on the keyboard, we get a C output on the speaker. You can also tell that the response is fairly instant because we're generating the note on the fly. This is a square wave, which is one of the most basic wave types that can be output. So really, in essence, this is just, so far, a basic MIDI player. However, we also put some extra bells and whistles on it. You can see that it has 4 notes of polyphony. And it can also play every note from A0 up to C7, which is the vast array that MIDI can generate. Now, the issue is, while we can play a lot of notes, there's not much variety so far in the types of sound that can be produced. That work is done through a synthesizer, which has a variety of parameters which can be modulated in order to produce complex sounds. This audio processing tends to be very intensive, and so a lot of the solutions are expensive and really fall into 2 classes: software synthesizers and hardware synthesizers. Hardware synthesizers are great for performance. However, a lot of times they lack versatility. In contrast, software synthesizers can play a variety of notes and can do all sorts of modulation and don't even have to run in real time. However, their biggest downfall is their lack of portability. We aim to solve these problems by combining the best of both worlds in FMPGA, a parameterizable, modulatable synthesizer with over 40 parameterizable options. This device aims to capitalize on the benefits of both hardware and software in order to produce the same diverse range of modulation offered by software with the portability offered by hardware. We do this by leveraging the power of an FPGA in order to generate complex audio algorithms that are used in software, while doing them quickly enough that we can put it in one hardware package. It's time to leave the computer behind. It's time to move to the FMPGA.
When a key is pressed or released, the MIDI keyboard outputs a serial UART bit stream that indicates the status of the note name, and the velocity, or in other words, how hard the key is being pressed. UART is an unclocked protocol, so we needed a way of deriving the bit stream accurately. Since it arrives at a known frequency with a known error range, we are able to estimate how many clock cycles the FPGA needs to wait until it receives the bit. Then we can count that number of clock cycles, sample the bit stream, use the rising and falling edge of the bit stream to recover the possible drift in the clock domain difference. Once the bit stream is sampled, we can parse those bits on an FPGA and decode them according to the MIDI protocol. This protocol is quite complex. We don't have to worry about this many types of messages. Instead, we can filter them for only note on and note off messages, which let us know what sort of keys are being pressed. When these events are detected, the frequency and velocity are extracted and passed to the audio processing unit, or the APU for short. In order to be able to play 4 notes at once, or in order to accommodate for 4-note polyphony, there are 4 APUs. We created an event scheduler that routes the MIDI packet to the least recently used APU that is not currently processing the note. If all the APUs are busy, it routes the note to the APU with the least recently experienced note on event.
By itself, the MIDI keyboard doesn't do anything interesting. In order to produce sound, its key presses must be interpreted and translated into a waveform. The FMPGA contains 4 APUs, which allow a user to play up to 4 notes at a time while having complete control over the sound they produce. Each unit contains a pipelined audio processing architecture with the ability to modulate pitch, amplitude, and distortion, and is easily scalable to modulate any other desired audio effects. The FMPGA provides 8 modulation sources. As you can see here, there are 3 low-frequency oscillators, 3 ADSR envelope generators, 1 high-frequency oscillator, and a constant value dependent on the intensity of the note press. These sources are configurable waveforms that allow a user to change an audio parameter across time. So for instance, they might choose to scale the amplitude of the note by a configurable ADSR curve. If you would set the attack, decay, and release to 0, we're just left with the flat part of the curve, and it sounds like this. However, we can configure the note to have a ramp up, or attack, a ramp down, or decay, a sustained value, and a period of release after the note is let go. Here, you can clearly hear the 4 steps. Instead of modulating the amplitude, the user might choose to modulate the pitch using an LFO, which produces a vibrato effect. Or they might choose to change the amount of distortion on the output note. Or they might want the pitch to undergo vibrato and an ADSR while oscillating the amount of distortion. As you can see, with just 3 knobs, there are billions of possible combinations to explore.
The output from the FMPGA is a 3.3 volt digital signal, which is then passed through a 3.3 volt to 5 volt level shifter, then through a digital to analog converter using SPI or serial peripheral interface, then passed through an op-amp to buffer the output, and then into a 3.5 millimeter audio jack as output. The name of the input that you're modulating is shown in the upper left-hand corner, and the name of the value that you're using to modulate that input is shown in the upper right. There are bars on the display for each parameter showing the value from its minimum to its maximum. To interface with the FMPGA, we provide an input using 3 encoders and a visual indicator of the parameter's values using an LCD display. Each encoder has a different purpose. The leftmost encoder lets you switch between pages of parameters. The middle encoder lets you change between each of the parameters on a certain page. And the right encoder allows you to change the value of a specific parameter. The inputs from the encoders are fed directly into the FMPGA, and to communicate with the display, we use SPI. So I'm just going to go through the process of making a sound very quickly. You won't be able to see my work on the display because the contrast is very high on this camera, but hopefully I'll try to narrate what I'm going through. I'm going to start by modifying some of the envelope parameters. So I'm going to turn up the sustain so the note stays louder for longer. I'm also going to turn the attack down so we get more of a stab sound than anything else. And then I'm going to turn the release down a little bit so it's just a little bit faster to get rid of the sound once we stop pressing a note. Once we're done with that, I'm going to move into the amplitude tab, and I'm going to move over to velocity, and I'm actually going to make the sound louder depending on the velocity that I play the note at. So that'll give a very lifelike sort of sound. So you can tell that we're sort of just starting out with a regular old sine wave. Nothing too fancy there. What I'm going to do next is I'm going to move to the distortion, and I'm going to maybe turn it up a little bit. Move to actually the distortion K, which is the level of distortion, and turn that up a little bit. So that's just going to bring out some of the harmonics. And then by affecting the dry wet, I can really get more of a square wave or a sine wave. So you can see I'm already coming up with sort of an interesting sound. I can modulate the dry wet using an envelope. And so what I'm going to do is I'm going to actually make it wetter based on the envelope. That'll make it just so that as it fades out, it just gets a little bit less modulated, which is going to be just a slight touch up there. I'm going to move that now over to the LFO tab. I'm just going to turn the frequency of the LFO up very slightly. Then I'm going to go into the pitch tab and actually modulate the pitch based on the LFO. What that's going to do is give a little bit of a tremolo effect. So you can see it's kind of a bit of a wonky sound. Now I'm noticing that the attack's a little bit, or the decay's a little bit too quick. Yeah, so just a slight touch there. And now I sort of have a really interesting pattern for making chords. You could or you could see maybe if I go higher. This could be a really interesting lead sound as well. And so that's an example of how to make a completely original sound on the FMPGA.